Hello everybody. Last time we started talking about scheduling algorithms for the interactive systems. Okay, we looked at I wonder what's going on. We looked at round robin scheduling, which is the simplest form, and then we said that not all processes are created equally. Some processes maybe should have higher priorities, and we were looking at priority scheduling. That's what we did last time, and we are going to continue and cover up all the other types of scheduling algorithms for the interactive systems. So one thing for the round robin algorithm is the quantum length. Quantum is the allocated time for each process. After the quantum time elapses, an interrupt occurs, and the operating system handles the interrupt, and it preempts the process that is using the CPU. We know this. So, and the length of the quantum time is important, and there is a trade-off. What is the trade-off? Trade-off is between system efficiency versus the interactivity or the responsiveness. Okay. So that's what we talked last time. Then we talked about priority scheduling, and we said that it is important to know the effects of the priorities, and if the priority scheduling is not implemented right, then we have a problem. For example, this priority inversion can happen, and this is the problem of, remember, policy enforcement. Where is policy enforcement? I think we talked about, yeah. So goal in all our scheduling systems are fairness, balance, and policy and enforcement. And policy enforcement says that give preference to work that is administratively favored, that is favor the processes that have the higher priorities. But, and while doing this, of course, we should prevent subversion of OS scheduling policy. And if we don't implement the priorities correctly, we may end up having this problem of priority inversion. And that's what we are talking about here. And in fact, I talked about this last time, so that's an important topic. Okay. Priority queues means that I have many classes of priorities. For this case, I have 3 classes: high priorities, medium priorities, and low priorities. And each one is run using a form of round robin scheduling. So there is a round robin going on here, another one there, another one there. This priority queue and this priority list and this priority list doesn't get any CPU time if there are processes in this priority list. That's what we talked about. So that means that there might be a problem of infinite overtaking or starvation. If we have always high priority tasks, these 2 processes or this process will never get any chance to use the CPU. And this may not be a good thing, because, well, I mean, low priority doesn't mean that they are not going to run at all. Low priority means that they will use the CPU, but they will use the CPU after the high priorities. But if there is always a high priority task available, then what am I going to do? So that's a problem. So they invented this. Okay, They said that maybe the priorities should not be constant. Okay, maybe the priorities should not be constant. Maybe we should adjust the priorities. Okay, what do we mean by this? We say that, okay, for each process we allocate a quantum time. Okay, for each process we allocate a quantum time. Yes, that's true. If the process is not using the complete quantum time, then that means that that process needed some input output or similar stuff, so it is blocked. So that means that that process is not getting enough CPU time. Maybe we should adjust the priority of that process so that when the data is ready, it has the highest priority among the other processes. Okay, so this is one technique here. If I used, if I used, are there any questions? Is somebody asking a question?
No, we cannot see your screen right now.
You cannot what?
See your screen.
You cannot see my screen, but you waited for 10 minutes.
No, I think we were listening to you, just rephrasing the past lecture, so we didn't say anything.
Okay, thank you. So, we said that, let's say uh, I I I I have a quantum time of, let's say 100 milliseconds. 100 milliseconds quantum time, right? Okay, let's say I have used only 25 milliseconds of it in my last allocated slot. Okay, so I didn't use the whole quantum time. So that means that I needed something from the operating system, from the input output devices, or I am waiting for some kind of a mutex or something. Okay, so I only use of the one fourth of the quantum time. That means that maybe I should increase my priority by 4. So it is 100 over 25. 100 over 25 is okay. 100 over 25 is 4. So I will increase my priority. Operating system increases my priority by 4. Okay, so there is an example. If I use 1 over f of my last quantum, so operating system boosts my priority proportional to f. Okay, so I set the priority to 25 if I use 1/25th of the fraction of the last quantum time. Okay, so that's one thing for the dynamic priority adjustment. So even if I am in the same priority list, I can have different priorities. Okay, so some of them may have higher priorities. Okay, so there are two ways of actually handling this. Okay, you either do a priority lists like this, priority classes, high class, medium class, low class. Okay, so that's one way of doing things. So for this one, I would only run the round robin on the highest priority list available. That's one thing. Okay, the other thing we are gonna come in a few minutes. So each each priority queue is run like each priority queue is run like a linked list. Okay, if I like to increase the priority of this process number 7, so what would I do? I would just take this node. I would just take this node and link it here. Okay, so I adjusted priority with the run queues. Okay. Okay, but this is the case for the run queues. Okay, but if we don't have many processes, Okay, maybe we can do a better job. If there are not many processes, we may have a fine-grained counter for each process. Okay, and we increase the priorities of the not running processes by using that counter at each clock interrupt. So clock interrupt, how many times the clock interrupt happens in a second? How many times a second the clock interrupt happens?
1 second divided by the quantum time or the average quantum time.
No, no, no. Quantum time and interrupt intervals are not the same thing. No. Interrupts always happen, whether you have a predefined quantum time or not. Quantum time is different from interrupt time. So how many times a second the interrupt happens? It is system defined. Usually we have 50 interrupts or 100 interrupts, something like that. Okay. That doesn't mean that our quantum time is the same as is the duration between two interrupts. No. Okay. So if we don't have many processes, for each process we have a counter. Okay. And at each clock interrupt, okay, we increase the priorities of the not running processes. So when the process get aged, okay, it is aging, so we know that that process did not run. Okay, but if we have many processes, this is going to take lots of time, because if we have many processes, 100 times a second we are incrementing this counter for all the hundreds of processes that we have. That's not going to be good. So we do the same counter for each priority list. So there is a counter here, there is a counter there, and there is a counter there. Okay. Of course, for the high priority tasks, the counter is not meaningful because they are already running. So the run queues with the priority adjustment may work this way. I'm not saying that this is the only way or this is the practical way. Okay, so this is the same picture from the book. Okay. Another priority related adjustment is the quantum time. Okay. So we know that many processes don't use the CPU time allocated. They don't use, or they cannot use, the CPU time allocated, the quantum time. Okay, especially the interactive processes. They need the user input. They don't have anything to do, so they just block. But as soon as the user input is available, they need to get the CPU and run. But we know that, so that doesn't mean that let's adjust the quantum time for the system wide. Okay, make the quantum time small, so we don't waste CPU time for these kind of processes, and the whole system stays responsive. No, we don't do that. Okay, because that would be very inefficient. Setting the quantum time low, okay, small values, means that there will be lots of preemptive switching, context switching. That's inefficient. So the solution is this. Okay, give lower priority queues longer quanta. Okay, so low priority tasks, usually they are not interactive, and they don't stop using the CPU while they have the CPU. So this is usually the idea. For the top priority queue, which have the interactive processes, we assign only one quantum, maybe 20 milliseconds. For the second queue, okay, lower priority, we allocate 2 quantum times, okay, 2 quanta, okay, and for the third one 4 quanta, etc. Okay, so that means what? The high priority tasks will have smaller quantum times. They are not using the whole quantum anyway, so they are going to switch. So that means that we are doing something already what they are doing with the lower quantum times for the high priority task. They will stay interactive. Low priority task which should not be interactive. As soon as they get the CPU, they like to use CPU as much as they want. Okay, because they don't need I/O most of the time. They are usually CPU bound. Okay, note that we are not by priority. Priority doesn't mean that one process is more important than the others most of the time. Okay, priorities are good for adjusting the CPU time, making system always be interactive. Okay, interactive processes are important, of course, but non-interactive processes, CPU bound processes, are also important too. Okay, with this case we are trying to achieve both: stay interactive, also keep the CPU efficiency at a high point. That's what we are trying to do. Okay, good. So we keep talking about the interactive processes. So how do we know that the process is interactive? How do we know that the process is interactive? We may ask the programmer to declare that the process is an interactive process, but you would not know if the process is interactive for the whole time, right? Think about an Excel program, okay? Excel program is very interactive. You will say that do this, this, and this, and this, and sometimes you would let a script run for 5 minutes without any interruption from the user. So Excel program could be interactive for a while, but it could be non-interactive for 5 minutes maybe. So we wouldn't know. So that means that we may have to adjust its priority or the quantum time from time to time. So what do? They used to do this. They look for signs of user input for that process. Okay, if that process is interacting with the user, okay, if that process is interacting with the user, it needs the mouse input, keyboard input, etc. In that case, I am going to assign higher priorities to that process. Okay, previously in 1960s, 80s, you have one large mainframe computer, and there are many terminals connected to it. These are the terminals, okay, and people are using this. One person here, the other one is there, the other one is. So these are just dumb terminals. So all the programs, all the processes are running here. So this is my main memory. So this is process 1, process 2, process 3. This is user 1, user 2, user 3. So each process should get a priority. How do I adjust the priorities? If the user 1 is using an interactive program, a word processor, maybe P1 should be a higher priority. If user 3 is running a numerical application which doesn't use any interaction, maybe its priority should be lower and higher quanta. Okay, so this terminal says that there is lots of interaction going on for this terminal 1. So the process is running with the terminal 1 will get higher priority. That's what they used to do that. But they invented this. This user noticed that even though he is running a numerical application, okay, he's running one CPU bound process. From time to time, every other second, he just hits the enter button. That's it. I mean, without any meaning, just hits the enter button, and this terminal 3 thinks that it is running a interactive job. So it increases the priority number for this task, even though it's an interactive. So those kind of hacky solutions were developed by the programmers. Of course, nowadays everybody is using their own computers. We don't use the remote computers with the CPU servers like that. Interactivity is not that important with the remote processes because we handle all the interactivity locally. Okay, so helping interactive process with the priority adjustment is some solution. They developed earlier. Okay, good. So how do we adjust the process priorities other than the interactivity? Okay, sometimes administrative issues, system performance is important. Okay, for example, kernel processes up to a point, of course, not always. Up to a point should have higher priority. Why? Because, for example, interrupts should have the higher priority. Why? Because I have to handle the interrupt whenever it happens. Because somebody is waiting for data, and if I don't handle the interrupt, maybe the IO device will stop working, and maybe there is a chance of missing the interrupt if I don't handle it. Okay, some kernel processes up to a point, okay, should have a higher priority. Of course, we talked about the interactivity. Okay, interactivity. Sometimes people say that, okay, I am going to be nice and I don't need the priority, and I am not an interactive process. Even if I am an interactive process, I will lower my priority using, for the Unix systems, using the command nice. So you are being nice to other processes. You say that I am going to run nice. I am going to run my a.out with a lower priority value. Okay, and you can specify even higher numbers of nice by specifying the niceness value. Higher the niceness value, nicer you are. Okay, so option is this, -n. So default is 10. If you say nice a.out, you are nice and your degree of niceness is 10. And if you say nice -n 100, you are very, very nice. So you can wait until all the other processes are done. You can specify a minus nice value, but to do that, you need to be the super user. Okay, so it looks like for Unix, the niceness can change from -20 to +19. Okay, good. Unix priorities are marked in a way that lower numbers indicate the higher priorities. Lower the number, higher the priority. And if you say a nice value of +19, it's a very low priority, and only the super user can set negative niceness. Default is 0. Okay, good. So I think this is, I don't remember, maybe this is from the book, or I think this is from the book. These are the priorities. Lower the number, higher the priority. So the highest priority is here, this one. Another one, very low priority is this one. And it says that PRI value factors is the niceness and the process's dynamic priority. Okay, good. So this is all about I am going to talk with the priorities. If there are no questions, then I will start talking about shortest time, shortest process next. Any questions? Remember, with the batch operating systems, we didn't have many choices for the scheduling. Okay, the simplest one was first come first served. Okay, it was very simple to implement. Then we talk about shortest process next, right? And somebody had asked me, how can we know the process duration without running it? And our answer was, you could know it because these are the batch processes, and batch processes are not run only once. They are run once a while, every week, every day, every month. So you know the statistics. You know the statistics. And if I have 10 million customers, and if I am going to print the invoices of those 10 million customers, I know how long it's going to take because I did the same thing last month. A little bit more, a little bit less, but I know. Let's apply the, so why do we do the shortest process next? What is the advantage of shortest process next scheduling for the batch processes? Question: what is the advantage of shortest process next?
We can push more processes through the same amount of time.
Our turnaround time, average turnaround time is favored, right? So if I do the shortest processes first, those short processes, they don't have to wait for the longer processes, right? You remember that, right? So if I have A, B, and C, handle A and B first so that they don't have to, both of them, they don't have to wait for C. Okay, if I handle C first, A and B has to wait for that long process. C is long anyway. Okay, so that was the idea. So what is the idea of shortest process next for the interactive processes? Okay, the idea is again the interactivity now, because we don't talk about these kind of processes. It is the interactivity. Whoever is short should get the CPU first so that it can stay interactive. Whatever it needs a very small amount of CPU time anyway. But then for the interactive jobs, having this kind of, okay, this is going to take 10 seconds, this is going to take 12, this is going to take 30 seconds. Having these kind of time guesses is not that easy because these are interactive and the users are involved. With the user involvement, you don't know how the process is going to behave. Do you know how long you are going to use the word program? You don't, right? It changes from time to time. Sometimes it's very short, sometimes it's long. So how am I gonna know the process time for the process? We can have a good estimate from the history again. We are going to do this decaying average. Okay. Let's say that the first time I ran it, it used T0 time. The second time I ran it, it used T1 time. Let's say T0 is 25 milliseconds. T1 is, let's say, 10 milliseconds. Okay. So it used 25 milliseconds out of its quanta. T1 is 10 milliseconds out of its quanta. That's what they used. So for my third run, this is my estimate. Alpha is something between 0 and 1. Okay, if alpha is 0.5, then what I am doing is 0.5 times 0.5 times 25 plus 0.5 times 10 is going to be, and alpha is 0.5 as I said, is going to be 35, okay, 17.5 milliseconds. That's what I'm expecting T2. Okay. Now switch T2 with T1 and T1 with T0. I am going to do this with T3. T3 is going to be 17.5 times 1 over 2 plus 25 times 1 over 2. Okay, that's what I'm doing here. So if you expand this expression, this is what you get. You are multiplying T0 with alpha square. T1 is alpha minus alpha square. T2 with 1 minus alpha. So since alpha is between 0 and 1, alpha square is much smaller than alpha. Alpha. And if I continue this way, alpha cube is much smaller than alpha or alpha square, right? So that's why they call it decaying average. So for T4, T0, the weight of T0 is very small. It decayed off. Okay. For T4, the value of T0 is not that important because I am multiplying it with alpha cube. And this is just a simple addition and multiplication process. So you don't do this kind of stuff. All you do is you always switch your T0 and T1 with the new values. Okay, so this is, again, the idea is the same. Shortest process next, and with the shortest processes, you continue with your scheduling for the interactive processes. Again, this is the idea is same as the batch processes, but the implementation is a little bit different, and our motivations are a little bit different. Usually the shortest process means that it needs more interactivity. It needs to interact with the user a lot. It needs a user input, a mouse input. It is sending something to the user, etc. Okay, good. Any questions? No questions, then I continue then. Another scheduling topic idea is guaranteed scheduling. Okay, the idea is this. If I have n users or n processes on a system, okay, I say that I should assign 1 over n value of the CPU for each process or for each user. Okay, if I have 10 processes, that means that every second 1/10 of the second should be allocated for one of the processes. So how do I calculate the processes CPU time? Of course, I would look at the statistics section of the process table. At the process table, I know how much CPU it has used. Okay, if that process is below this value, 1/10 of a second CPU usage per second, then I should put that process in front of the others. Okay, so I should maybe increase the priority of that process with some value. If that process had used more than its fair share, okay, then I am going to lower its priority. So that's called guaranteed scheduling. Okay, this n is either the number of processes or number of users. Okay, if there are 5 people using my mainframe computer, remote computer, maybe I should schedule, maybe I should adjust my scheduling times this way. Okay, this is called guaranteed scheduling. Another scheduling, creative scheduling idea is the lottery scheduling, piangability, lottery scheduling. Let's say you have 3 processes, process 1, process 2, and process 3. Okay, 3 processes, process 3. And this one has the highest priority, middle priority, and low priority. You will say that I have a total 10 tickets in my hand. 10 lottery tickets. 10 tane piyango bileti. I have 10 tickets and I will give 5 tickets, okay, 5 tickets for this process, 3 tickets for this one, and 2 tickets for this one. There are a total of 10 tickets. Now I do the random picking of number from 1 to 10. Okay. Who has the highest chance of winning the lottery? Of course, P1. Okay. But that doesn't mean that P1 is going to win the lottery. Okay. It has the highest probability, but it doesn't have any guarantees, right? Even this one, which has 2 tickets out of 10, okay, has a chance of getting the CPU. Okay, so at scheduling time, we just pick a random ticket from 1 to 10, and we know that P1 has the highest chance of getting the lottery. Okay, so this is a very nice way of, very efficient and nice way of doing the priority scheduling. And the nice thing is that there is no starvation. Okay, remember with the priority queues, okay, if these are all runnable, these will get the CPU all the time. Okay, if these are all runnable, these will get the CPU all the time. This priority class or this priority class will not get any CPU time if you are applying the strict priority queues. Okay, to prevent this, what did we do? We said that maybe we can increment the priorities or decrement the priorities, and etc. We did that. With the lottery scheduling, okay, we don't have this problem. Why? Because P3 always has a chance of getting the CPU. It might be a small chance, but there is a chance. Okay, that's what we want actually. Most of the time we like to give priority to the P1 process. And the nice thing is that, okay, the tickets can be exchanged between the processes. Okay, tickets can be exchanged between the processes. Remember the priority inversion? Can you tell me a solution for the priority inversion using the lottery scheduling? Give me a solution for the priority inversion problem using the lottery scheduling technique.
Maybe one process taking the CPU time, we reduce its process ticket.
That's a good way of adjusting your priorities for starvation, but I am talking about priority inversion. Let's remember the priority inversion again. What was the priority inversion? Can anybody tell me? It usually happens with 3 processes like this. P1, P2, P3. I think I talked about this 3 times. Anybody? No? Nobody remembers the priority inversion? I started my today's lecture talking about priority inversion.
Priority inversion is when one task doesn't get executed because lower priority task, one lower priority task doesn't get executed because constant influx of higher priority tasks.
No, that's called starvation. Okay, at 11:30 today, 11:30, I will give you a quiz, okay, an online quiz, and I will ask 2 or 3 questions for 10 minutes. It looks like nobody is listening to me, so I will ask these kind of questions then. Okay, at 11:30 today, I am going to give you a small quiz for 10 minutes. Okay, again, for the 4th time, I am telling you what the priority inversion is. This is high priority, low priority, middle priority. Let's say high priority, it needs a lock, okay, a mutex lock. Mutex lock is not available, so this one is blocked. This one is blocked, okay. And that lock is held by this P3. Okay, this P3. This P3 has to run to release the lock, but this one cannot run because P2 is running. Okay, P2 is running. So P1 is waiting for P3. P3 cannot run because, even though it is ready, because P2 is running. So with the lateral scheduling, if P1 is waiting for P3, maybe P1 can give its lateral tickets to P3 so that it can run and it can release the mutex. Okay, that's what it says. Tickets can be exchanged between the processes. Okay. Another interactive scheduling idea is the fair share scheduling. Okay. They say that, okay, the scheduling adjustments between the processes doesn't make much sense. Why? Because the scheduling the priority should be happening between the users. Okay. So if I say, if I do the guaranteed scheduling, or if I do the lateral scheduling between these 3 processes, P1, P2, P3, let's say P1 belongs to user 1 and P2 belongs to user 1 again, and user 2 has the P3. Okay, so that means that user 1 has lots of advantage. So important thing is not between the processes. We should be careful about who owns what. Okay, if I try to do the fair scheduling between the processes, then user 1 can say that let me fork lots of processes. Okay, user 1 says that I am going to fork P1, P2, P3, P4, and user 1 has only one process, P5. Even if I am doing the guaranteed scheduling between all these 5 processes, okay, user 1 is getting 80% of the CPU time. That's not good. Okay, so fair share scheduling says that, okay, I don't want to encourage forking just to get a larger share of the CPU. So the solution is okay, I am going to make the decision based on the CPU consumption instead of the process CPU consumption. So I am going to increase the priorities and the CPU allocation times that way. Okay. So that's called fair share scheduling.
How is that going to happen exactly? Or how is that going to be implemented exactly?
How is that going to be implemented? Well, maybe you can use the priorities. Okay. The larger the forking number for the user one, the lower the priorities of those processes. Let's say the priorities of user one and user two is the same. Okay. If I have a single process for user two, okay, P5 should have the highest priority, the most number of lottery tickets. Okay, if you are talking about the lottery tickets, maybe this one should have 8 lottery tickets, and this one should have 2, 2, 2, and 2. Okay, so in total, user 1 and user 2 had the same chance of getting the CPU. Of course, P1 has the highest chance of getting the CPU. P1 is lower, all right? But that's expected because there are 3 more processes of U1.
But if you think about it, maybe U2 is listening to music while U1 is training a neural network model. So U1 would need more CPU power.
Of course, these are not single dimensional decisions. Okay? These are not just single dimensional decisions. You have to think about the interactivity. If U2 is running a numerical application and all the process of U1 is interactive processes, and we said that interactive processes should have a higher priority. I am assuming that all the processes have the same type of processes. They are all interactive or non-interactive.
I see.
Okay, so if you mix all kind of factors together, of course you wouldn't say like the regularly this is 8 and this is 2 and this is, so you are incrementing and decrementing those numbers, incrementing and decrementing those numbers by considering both this fair share scheduling, interactivity, shortest process first, etc. That's why we have this kind of weird numbers here. Like you don't see just a 60, 70, 70, 50, etc. Right? There are 76, 75, 83. So, and the consequence of adjusting these priorities may not be very apparent. You have to run experiments to see what kind of effects you are getting. Okay, I think I am done for the first part of the lecture. We will start at 11:32, and for 10 minutes you are going to have a quiz. I think you will have 2 or 3 questions. You are going to answer them, okay? Okay, see you in 10 minutes. I need to prepare the quiz now. Okay, that's not the case, no. That's not the, Tugay, just turn off your microphone, okay? Turn off your microphone. I'm not talking to you. I am talking to other people, okay? That doesn't mean that you are at a disadvantage, okay? This is just a course. Whatever you learn is yours. Grade is, Tugay, just turn off your microphone, okay? So that doesn't mean that you are at a disadvantage. Do an honest job, and you will see at the end that you are the one that's gaining. Okay, let's go back to the lecture. So ours is fair share scheduling. We talked about the fair share scheduling, and let's
Sir, we cannot see your screen.
yeah. Let me turn. Okay. In fact, let's go back to the questions and let's go over them. And what did I ask? Let me open the. Okay. Where is my? Okay. So let me just open one. I'm trying to find the quiz. Sorry. I found that. Okay. Let me try to make it, and yeah. So this is somebody's answers. I am trying to hide the name if I am. Yeah, okay. I hid the name. So the question: how do you prevent priority inversion using priority lists? And during the lecture, I asked you how do you prevent the priority inversion using the lottery tickets. Okay. So this person says that give a lower priority quiz, longer quanta. That's not going to prevent anything, because priority inversion means that high priority jobs are waiting for low priority processes. This is not going to prevent it. The one solution could be this. If a high priority job is waiting for a low priority job, okay, and the operating system knows it, it is blocked that. The one logical solution is to change the priority class of the low priority task so that it can continue and it can release the lock. Okay, so it is like giving the lottery tickets, but this time you are changing the priority class. So the second question is, why can't we implement the word processor application with 3 processes instead of 3 threads? So the answer is, well, I mean, if you try hard you could, but the idea of 3 threads with the word processor application is, one is doing the interactivity, the other one is doing the screen management, the other one is doing the backing up. So they should use all the same address space so that they can share data. The processes, they don't share the address space. Okay, so which one is better, lower quanta values or higher quanta values? Of course, this is my question, right? None of them are better for a single purpose. Lower quanta values are good for interactivity, higher quanta values are good for the CPU usage. So it depends on what kind of application you have, what kind of processes you have. That's what I was expecting. Okay, any questions about the questions?
Sir, for the second question, I have wrote something lines of the quanta values being different for different purposes. Well, I didn't say especially quanta values, but
Yeah.
different processes require different times. So
Yeah, but I mean,
processes may
you
have.
should talk about a little bit why this is the case. So I mean, yeah, I mean, there is no single quanta value for system-wide global quanta value. That doesn't make much sense, because lower quanta value doesn't make sense for the CPU-bound processes, and the higher quanta value doesn't make sense any for the interactive process. I mean, the examples would have been much better.
Okay, thank you.
Sir, I write something for question one for the priority inversion, preventing priority inversion. The sentence that dynamic priority allocation can solve this problem.
Yeah, but
Is it
how? Yeah, that's dynamic priority allocation solves it, but how? The idea is you need to determine what causes this priority inversion. A high priority task is waiting for a low priority task to release the lock, right? So you
yeah.
need to detect it first, and do your dynamic priority adjustment between those two tasks.
Yes, sir. I mean,
Okay.
yes,
Okay, good. So let's go to our slides again. Real-time systems. Real-time systems. So with the real-time systems, the important things are these. We already have seen it. Meet the deadlines. There are deadlines, and you are going to meet them. It has to be predictable. What do we mean by predictable? I mean, computers are deterministic things, right? So what is predictable? But with the world of computers, lots of things are going on, especially with the parallel processes running, and many things are happening, user interaction and etc. Okay, everything is deterministic, but that doesn't mean that the response times are going to be predictable. Using Word, sometimes when I click a button, I get the results immediately. Sometimes it takes a few seconds, right? So this is not predictable. Okay, as a user, it is not predictable. So real-time system says that, okay, when I say something, when I say, okay, format my screen, it should always take 20 milliseconds, okay? No more, no less. Okay, maybe less could be acceptable for some cases, but more cannot be accepted. Okay, so it needs lots of careful engineering. Okay, there are two types of real-time systems. The first one is the real-time systems, hard real-time systems. That means that there are absolute deadlines that must be met, or the whole system is a failure. That's not acceptable. So that's called hard real-time systems. Okay, hard real-time systems. And those hard real-time systems, every process should have their own amount of time to use the CPU, and you cannot use more CPU time. And as I said before, real-time systems are not preemptive. They cannot be preempted. They cannot be preemptive. Why? Because if a process is supposed to run in 20 milliseconds, it is supposed to run in 20 milliseconds. That's it. The operating system shouldn't come in and after the interrupt should say, I am going to block you right now. No, I am going to put you in the ready queue now. Okay, but for the soft real-time systems, you may miss some task from time to time. We don't like it, but it is still acceptable. Most of the multimedia applications or multimedia systems, for example, the sound system in your car, okay, or your television set, okay, is a soft real-time system. Why? Because your television has to show you 30 frames per second. Okay, when you hit the remote, I have a remote here. When you hit the remote buttons, it has to respond in like 5 milliseconds and etc. So we have these kind of deadlines, but what happens if I hit the OK button on my remote and it didn't respond in 5 milliseconds, but instead in a second? So I would tolerate it. I would say that's a bad TV set, but that doesn't stop me from using it. Okay. But for the hard real-time systems, your ABS brakes should always work when you hit the brake pedal in your car. Okay, your brake should always work. There are no exceptions. There are no exceptions. Okay, so with the real-time systems, actually, most of the time you calculate this. Let's say I have three processes. Process number one, and process number 2, and process number 3. Okay, process number 1 happens, let's say, every 200 milliseconds. Okay, every 200 milliseconds, process 1 runs, and it runs maybe for 50 milliseconds. Okay, process number 2 runs every 100 milliseconds, and it runs for 10 milliseconds. Okay, and process number 3 runs 150, and okay, every 150 milliseconds it runs, and it runs for 30 milliseconds. So the idea is this: can I support these three processes for my real-time system? Remember, I cannot delay them. I cannot say that you are going to wait for this and this and this, okay? You are going to wait for 5 seconds and etc. So what you do, you say that 50 over 200, so this is taking only 1/4 of the CPU time, plus 10 over 100 plus 30 over 150. So how much does this make? Can I, okay, how do I 100, 600? So this is like, get these out. So 60, right? 60 is the common, the smallest multiple of these, right? Yeah, 60. So 315 plus 6 plus and 12 over 60. This is 21, 33, yeah, 33 over 60. So it is almost 50%. Okay, so as long as this is smaller than, as long as this is smaller than 1.0, we are fine. Okay, so this is how you calculate your load times, your load factors. Okay, and this is the formula actually. Event I needing Ci seconds of CPU and occurring every Pi seconds or milliseconds. So you divide them Ci by Pi, you add them up, and it should be less than 1. Of course, you should consider the switching times too. There will be context switch time. With the periodic events, that's what happens. That's what happens. Okay, so usually very specialized computers, like computers on the space vehicles, okay, they don't do much actually. I mean, with the space vehicle, what do you have? Let's say this is your satellite. Okay, with your satellite you have your the sun panels to produce electricity, and you have your thrusters to adjust your altitude and attitude, etc. What else? You have your antenna pointing towards Earth, and you have cameras. You have cameras to look to the sun or the stars. So now this look like a person, right? So to make it complete, let me put this like that. Okay. No green stuff there, but just okay. So there are 4, 5 devices that you need to consider. Okay, are my thrusters okay? Am I looking at the sun right? Is my communication to the world is okay, and etc. So each task gets a CPU time, and you are in a very careful way. Okay, yeah, a careful way. You are engineering your tasks. Okay, this is not a general purpose computer. After your real-time operating system is designed and it is tested, you are not supposed to add new tasks to it. All the tasks are fixed for the hard real-time systems. Okay, so this is the same example that I did. So 50 over 100, 30 over 200, 100 over 50 is less than 1.0. So these are all schedulable real-time systems. Of course, we talked about these periodic events. We say that P1, P2, P3 always happen 200, 100, and 150 milliseconds. We know that. What happens? There are what if I have aperiodic events? Okay, if I have aperiodic events, in that case, I have to be more careful because these don't happen every 200 milliseconds or 500 milliseconds. So engineering such systems is harder. Why? Because I don't know how many times it's going to happen, and I don't know how long it's going to take, and etc. Usually, you would say that I will not allow these kind of processes, these kind of events. Okay, so either you are happening periodically, or I am not going to let you run on my system. Okay, so at the end, what you are trying to do is total load must be less than total capacity. Usually they say that, okay, this number less than 1.0 is the absolute limit. Usually you would want something around this. The load must be less than 0.75 because in case of emergency something happens, there's a problem with the computer system and etc. I should be able to cope with those kind of unexpected cases. Okay, and these are the real-time systems. Any questions about the real-time system scheduling? Well, I didn't say anything about real-time scheduling actually. What did I say? I said that if I have 4 processes, 1, 2, 3, 4, 25 milliseconds for you, 50 for you, 30 for you, and 20 for you. Okay, so I make those decisions at the beginning of my system design, and scheduling is done that way. Okay, it is always P1, P2, P3, and P4. I don't have the luxury of thinking and trying to make a decision on which one runs first in the hard real-time systems, because you cannot run those kind of algorithms in the operating system of the real-time systems.
So, like the aperiodic things or aperiodic events, they are like the emergency case events.
Well, if you have those kind of events happening, okay, you will say that P4 is my emergency process, and I know that 99% of the time it will not do anything, but I am still allocating 20 milliseconds of my 100 milliseconds for that one.
Oh.
Even it happens once a year, I am going to handle it and I have time for it. So you are wasting 20% of your CPU time, that's okay. Real-time systems are not easy, cheap systems. Okay?
Sure. Also, we don't talk about context switch here.
Sure, yes, there's a context switch. When you are doing the context switch, remember, okay? So context switch time in this calculation is included in this 50, 30, or 100. There is context switch always, of course.
But we don't calculate here.
Well, but that's what I said. I mean, out of this 50 milliseconds, maybe 10 milliseconds is for context switching. So it is included in the event handling. Understand?
Okay, thank you.
Mm-hmm.
Yes, thank you.
Good. Any other questions? Context switching is going to be very important. You might think that what is the big deal about the context switching, but it is so important. Why? Because one thing, I think I showed you this before. One thing is invalidation of the cache. Do you remember these numbers, right? You remember these numbers? If you are getting all of your data from L1 or L2 cache, we are talking about half a nanosecond or 7 nanoseconds. L1 cache is small, but you can fit your average loop in L1, and in L2 you can do that too. So you are very fast with the L1 and L2 level caches. But if you need to go to the memory, even for a single word, you are going to spend, okay, 200 times more time for the memory access. And we are talking about a cache of a few megabytes, right? 10 megabytes of cache, 4 megabytes of cache, okay? For the L2 cache, okay, there is 15 times more cost in terms of accessing the main memory. So filling in the cache, megabytes of data, populating the cache is going to take lots of time. So if you switch from one process to another process, you are switching the address space, okay? So invalidating the cache and repopulating the cache is going to take lots of time. Okay, that's one thing. And we didn't talk about the lookup tables, virtual memory page tables, and they are megabytes of data to be loaded again, because those page faults are very, very expensive. So context switching is going to be important when you are doing the process thread processing, okay, scheduling. Also when you are doing the memory abstraction, your virtual memory. We will keep talking about the context switching. So it's a good thing that you are concerned about the context switching. Okay, without context switching, there wouldn't be no modern operating systems, because context switching is the fundamental part of the abstraction, the abstraction of the processes, abstraction of the CPU. But we don't like the context switching because it is so expensive. We cannot live without it, but we like to do it as much as infrequently as possible. Okay, good. So that's the end of the scheduling. One specialized topic, but important topic, about the thread scheduling. We talked about this a little bit. We said that there are two types of threads: user level threads and the kernel level threads. Okay, how does the thread scheduling work? Okay, first of all, there is no preemption between the threads. Okay, there is no preemption between the threads. If a thread takes the CPU, and if the thread wants to use the CPU forever, it is free to do so. Okay, if it is free to do so. Thread 1 takes the CPU, doesn't want to give up the CPU, it uses the CPU all the time. Thread 2 and thread 3 doesn't get the CPU at all. Operating system doesn't say anything about that, especially if it's a user level thread, because operating system doesn't know that there are 3 threads happening inside process A. But operating system knows that process A is a process, yes. If process A is using too much CPU time, and if it's an preemptive operating system, it will stop it from using the CPU and it will switch to process B. We know that. Okay. So that's something to keep in mind. If we are doing the user level process handling, thread handling, then this is a possible scheduling order. So this is thread A1, A2, A3. This is, okay, B1, B2, B3, and B4. Okay, so this is possible thread scheduling case. A1, A2, A3, A1, A2, A3. Okay. So what is the condition for switching from A1 to A2? What must happen to switch between A1 to A2, from A1 to A2 here? What happened as a result?
The process itself decides that I would switch, since process handling is like held by the process itself.
But the process is just a process. Process cannot make decisions, right? I mean, It is running. It is using the CPU. So who is using the CPU? Thread 1 is using the CPU. If thread 1 is using the CPU, A1, okay, so what is the condition for me to switch? What happened so that I did the switch? What triggered this switching from A1 to A2? You cannot say the process is doing it, because process doesn't have any capability to come in and stop A1. Like the operating system cannot come in and stop a process from running. The process has to ask the operating system to do something, or a timer interrupt should happen, right? With the threads, no such thing happens, okay? Because with the threads, I cannot say that a timer happened, then I am going to do it, because there is no preemption with the threads. So what happened between this A1 and A2? What caused the switch? Let me tell you the first one. The first one is thread A1 asked the operating system to load some data from the desk. Okay. Well, in that case, let's say it is asking this loading of data through the thread scheduling. So thread scheduling knows that it is waiting for us, so it is blocked. So thread scheduling made that decision to switch to A2. Okay, that's one thing. What else? There is no preemption. How could this switching can happen from A1 to A2? That would have been another good question for the quiz, actually.
Maybe thread yield function called?
Exactly, thread yield function is called. Remember the thread yield function? It's part of the thread library. These threads would call those functions. Okay, you will say that, okay, I am done. I am not going to use the CPU. Even though I could, but I am going to let other threads use the CPU. That's called cooperation, right? So there is always cooperation between the threads of the same process. So this A1, A2, and A3 are cooperating to do some tasks such as word processing. And B1, B2, B3, B4 are cooperating again. Process A and process B are competing. Okay, they compete. They think that the whole memory belongs to them. They think that the whole CPU belongs to them. They don't care about the rest. But thread 1, A1, A2, and A3, they say that we are sharing this memory together with two other threads. We are sharing the CPU with two other threads, and we are cooperating to do some task. Okay, that's why A1, A2, and A3, they should call thread yield from time to time. Okay, doesn't matter if it's a user level thread or kernel level thread. Okay, if the things are okay, so one says that this is possible, A1, A2, A3, A1, A2, but this is not possible. Why? Because A1, B1, A2, B2, A3, because, I mean, from A1 to B1, in this case, it needs a process switch. Okay, from B2 to A2, it needs a process switch. And the operating system doesn't know about the threads, so this is not possible. But if I am doing the kernel level threads, so this one is possible and this one is possible too. Both of them. Which one is better? Which one is better? The first line or the second line?
I mean, it depends on what kind of things you are trying to achieve or accomplish, isn't it?
I'm talking about the CPU usage, system efficiency. In terms of system efficiency, which one is better?
First one.
User level.
No. I am talking about the first line or second line. This is the kernel level threads, and it says that this scheduling and this scheduling is all possible with the kernel level threads. And I am asking you which one is a better scheduling choice in terms of CPU usage.
First one would be better because, like, it doesn't have to, change context as much.
Yeah.
Like in case of cache and stuff like that.
At least the address space doesn't change. That's not an automatic cache invalidation. If you switch from A1 to B1, the address space changes, you have to invalidate your cache. Okay? All the entries in your cache are now invalid if you switch from A to B. But if you switch from A1 to A2, you are already using the same address space. You don't have to invalidate the cache. Okay? Whatever you have cache hits, it will stay. So it is still expensive, but it is not as expensive as switching from A1 to B1. Okay? So if the kernel knows about this, kernel can make these kind of smart decisions. Kernel can make these kind of smart decisions. So if you are doing the kernel level thread scheduling, I would always prefer the first one to second one. But what happens if all of them are blocked? This one blocked, and this one blocked. They are waiting for something, or they are yielding the CPU. Then the kernel will say that, okay, nobody can do anything like in this process. And I am going to stop this, and I am going to put it in the block queue, and I am going to run this now. It can make these kind of smart decisions. Okay, so in this case, if the kernel is this smart, which thread handling method is better, kernel level threads or the user level threads? Or maybe can you tell me one important advantage of the user level threads that the kernel cannot easily achieve?
We have more control over our threads.
Yeah, explain that a little bit.
We can change the priority, and we can guarantee some threads work before than others.
Yes, exactly. I think we talked about this a little bit. In this case, there are 1, 2, 3 threads running, doing useful task, and there is another thread. It is called the scheduler thread. Okay, the scheduler thread is scheduling between these 3. Okay, so I think there was a good example here. Yeah, I think. So if I have a web page server like this, okay, this is process web, okay, there is a dispatcher thread, and these are the worker threads. I have 1, 2, 3, 4 worker threads. These are just answering the clients. If there is a web page request, there is a worker thread. So this dispatcher thread, these are the W1, W2, W3, and W4. This one, okay, dispatcher thread takes the request and assigns the request to one of these worker threads. Okay, one of these worker threads. So what do we do now? In this case, these are all threads, right? These are all threads. So there is a thread scheduler running here, a thread scheduler running here. If one of the threads are blocked, which one should run next? Okay. Of course, I know that the thread, the dispatcher thread should run next, because every time a worker thread is blocked, this one should run so that it can decide which worker thread is going to run next. So this kind of scheduling can only happen with the user level threads. Kernel cannot know these kind of decision preferences of the processes. The process does its own scheduling, and this is much more flexible. Maybe not that efficient, but it is much more flexible. So sometimes we prefer these kind of solutions over the kernel level threads. That's what we talked about previously, actually. Okay, any questions? Any questions? Okay, if there are no questions, tomorrow we will finish up with this chapter, with this dining philosopher's problem and the reader's writer's problem, and I will start talking about the memory. Okay, I'll see you tomorrow.
Have a nice day, sir.
Evet arkadaşlar.
Merhaba hocam, nasılsınız?
Teşekkürler. Sizlerden ne haber?
Bizler de iyi olmaya çalışıyoruz hocam.
Dersi bitiriyorum da bir dakika şunu bitireyim.
Tamam
Evet.
hocam, problem.
Söyleyin ama.
Bizlerin öğrenme dersi için yanlışlıkla.
Bir iki bir şey soracaktık hocam.
Tabii buyurun. Gelinsene, niye bekliyorsun orada? Bir dakika şunu bitirmezsem ben oturun ya. Bir yerlere oturun.
Şöyle oturayım.